Hi, this is Soumalya. I'll talk about activity recognition in PHM related service environment from EEG via deep learning. This work was done by me, my colleagues in UTRC, Kishore, Alex and Kelly mainly helped in data collection, and Michael. Um, this introduction was already done by my colleague Kishore about our company. What we do mainly we have climate controls and security, Otis elevators, and Pratt and Whitney aerospace systems in our products. I'll jump right into the problem. So the main question is why EEG in PHM related workshop, and PHM is, I know it has health monitoring in that, but it's generally for machines. Uh, but here EEG is used on human being for understanding the cognitive activity. So the main objective here is to actually, I mean, human is a main important part of the whole PHM process because they're in the service area and they take care of the whole process when doing any health monitoring or condition-based monitoring. They have to finally understand and undertake the process. So, and for that, there are very detailed training schedules and training modules and designed by the companies. And to design them, you have to understand how the human being, how the service personnel feedback is happening. So, what type of training module that person is liking, or what type of training module actually helps the person to concentrate on the job or on the schedule. And also definitely for safety enhancement because service personnel has to do a lot of things at the same time, and that person has to be attentive all the time. So how we can actually analyze the attentiveness or the kind of activity that person is doing without actually being very invasive, such that the person can do their own job. So mainly, how can you design a personalized training module, and also how can you enhance the safety? So for that, we need real-time activity monitoring at operational environment, not in a lab environment. That's one of the big challenges. And also monitoring them through different physiological measurements. There are other type of data also. Here we have selected EEG for different reasons. And also monitoring the performance level, which will help us to understand how the job was done. So very recently, some companies they have started putting the smart cap or this kind of technologies where there are some basic sensors which are trying to understand uh, the activity level, but not to that extent where we can actually use EEG on a full scale in the real-time environment. So, what are the main challenges of EEG and why EEG we are actually selecting? EEG is a very good sensor for brain computer interaction, and it helps. It's generally multi probe sensors. When we have 9 sensors, sometimes we have to the order of 50 sensors in EEG. And it helps us understand different activity through scanning the cognitive data. So the problem with EEG system in actually deploying in the real environment would be it is very bulky, and also the data is very highly noisy and highly transient, and also all the time we need baseline for where we are using it. We need the baseline for the specific person. So we have to be pretty adaptive in that area. So there have been many work in understanding EEG data for mainly classifying different type of activities, or mainly understanding the level of workload or level of attentiveness. So a level of attention. So mainly different types of work would be signal processing based methods like time frequency features, multi-resolution analysis on wavelet features, and bunch of work on neural network area. And this independent component analysis also another type of work uh, which was mainly centered around analyzing EEG data around 10-15 years ago. But every analysis they are based on baseline and also careful handcrafting of features. So here our main contribution is we're trying to classify different cognitive activity in real time, and using different types of deep learning techniques. And also, after doing that, we don't want to use all the EEG sensors. So how can you select those smaller suite of EEG sensors such that we can deploy it in real field, and but keeping the performance similar for that kind of tasks. And also we do performance validation and comparison. And finally, one of the problem of deep learning is it sometimes feels very black boxy kind of. We have no idea what it's learning. So we want to know what kind of feature it's learning, and with proper domain expert knowledge, we want to show that the kind of feature it's learning, it actually means something. It's not a garbage feature. It's some local minima it has learned, and we're just using that. So the main experiment was we used this 9 EEG probe sensors, and we collected baseline for mainly for calibration, not for the analysis part. And we had mainly 4 type of tasks where we had like watching video for different training modules. We had reading manual for training modules. So mainly we can class them as watching. Another class would be listening, so listening to music and listening to manual. And so we had hours of data mainly on 3 subjects. In the future, we are planning to extend that number of subjects a lot, but for now we have 3 subjects data, but we have at least 2-3 hours of data for each subject. And the sensors mainly we used 3 in frontal area, 3 in the center, and 3 on the back. And first task was whether from the data we can classify between watching and listening. So in real time, if we can actually classify that person is watching or listening or whichever it's concentrating on during a training module, that way we can design the training module in the future, maybe on the watching part or on the listening part, or we can emphasize on different types of cross modality in the sensing. So it's just a data snapshot. We had also heart rate data, but we did not use it in the analysis. We mainly used the 9 EEG sensor probe. So the main idea was to first classify between listening and watching from the EEG sensors. And we had 9 probes of EEG sensors. We did not directly use the time series data. After, in a window approach, we took a 5-second window. We tried with different windows, but we wanted to actually capture both slow time scale and fast time scale phenomena. We are not using any LSTM type of approach here. We used mainly more like a static network kind of approach here. So that's why we wanted a larger window size. And from that, through Fourier transform, we use 2 types of deep learner. Mainly one is DBN, deep belief network, another is CNN on the time series data. So for DBN, we use a contracting network where we had the input from the 9 sensors, and we contracted to 20 network, then classify between activity classes. And for the convolutional neural net, we mainly use the spectrogram, and we saw whether we can find some smaller structure features in the spectrogram, whether it will give more advantage than DBN. One interesting advantage, also kind of expected, was that the CNN takes a very small time to learn, and learn in the sense very small number of epochs compared to DBN to learn and to actually get the same level of performance. But DBN needs a longer time to actually reach that level of performance. So in the real time, if we kind of slide the window and see what is the activity classification accuracy, we can reach up to 91%. It's a very hard problem in the sense that if we actually want to classify 4 classes, it's better than coin toss, but it's around 50%, not more than that. We tried different types of method, but the data is really noisy, and and also there are a lot of shared features between different classes, so it will be hard to get to a very high confidence. But if you want to at least classify between listening and watching just from the EEG data without any baseline consideration, we can at least go to 90% of accuracy. And we compared with other type of techniques where we cannot achieve that much. And now we want to see the features, whether we are learning something significant or whether domain experts agree with it. So we had experts who have been working on EEG for a long time, so they kind of they have their expectation that, okay, when we have listening or we have watching, we have different frequency bands which are more important. So when we are listening and when you're watching, so there is an alpha dominance of P, the parietal sensor, the sensor on the back. They have alpha dominance, and while listening, it shifts to beta dominance. So there is this different frequency beams. They kind of attach different activities to those frequency beams, and they're saying whether this alpha dominance move to the beta zone, and we can see that in watching activity. And also we can see that there's a high gamma activity during watching, which we should expect, because that means we have a cross-modal type of activity. That is, we are seeing and also we are listening to it. There is cross-sensory activity going on. And here we visualize the feature in the deep network by actually percolating um, perfect classes from top to bottom. Like we have 1 0, we percolate to the bottom and see what is the type of frequency beams we are seeing. And then we also do a sensor selection from a backward point of view that says that we can actually capture pairwise effect also. And we come up with different sensors, sensor modules, sensor suite. And we can say that if we take the line of sensor from front to bottom, front to parietal zone, we have 3 sensors which can achieve similar type of performance for this specific task. And also we can see that the sensors on the back, they have also very high performance. Just if we use P3, PZ, and P4, they also can be very effective, and that is kind of expected because it's mainly related to watching and listening type of task, and parietal zones of the brain gets activated with cross-sensory type of activity. So that helps in our classification between listening and watching. So to conclude, I would say that we kind of train directly on time series without baseline knowledge and without feature handcrafting, kind of directly applied it to the network, and we achieved high accuracy. But we want to, experimenting with human is pretty tough. So we want to increase our test data set, and we compared to benchmarks, and we did feature visualization to actually understand what it's learning, such that we can scale it up. And also we obtained a smaller sensor suite, such that it will be more realistic to use in real field. And some future research tasks are mainly validation on more data and fusion among broader area of heterogeneous sensors, not just EEG, but this deep learning kind of, if you have similar time scale sensors, with this kind of network, we can feed in more different modality sensors to get a better idea of different activity in real time. Thank you.